All right, so I thought that we would proceed with looking at some practice problems from Chapter 13. So I've taken some problems from the back of the book here and copied them into this page in our OneNote drive, and I thought these were good ones to look at. So the first question here, we're asked basically to look at these equilibria. A and B under 17 here are the same equilibria, and we're asked to evaluate the reaction quotient, determine direction they'll proceed. Okay, so for A, we're going to write that the Q expression for this, we want QC, it's going to be N2 concentration, since it's C, times H2 concentration raised to the third power because of the coefficient, divided by ammonia's concentration squared because of that coefficient there. And then we're going to plug in our values. So N2 is 1, H2 is 1, that'll be cubed, and then NH3 is 0.20, and that'll be squared. So let me get my calculator out here. I think I can do the top part without a calculator. 1 times 1 cubed is going to be 1. And then I'm going to be dividing that by 0.2 squared. So that gives me a value of 25. Now if I compare that to the Kc, which is 17, 25 is greater than 17, so Q is greater than K. QC is greater than Kc. So what does that mean? That means if Q is greater than K, that we've got too many products, not enough reactants, so we're going to have to shift back to the reactants. So if I were writing my ice chart for this one, that would be NH3s into H2. Initial was 0.2, 1, and 1. Q we decided is 25, which is greater than Kc. Our change line then would be plus, minus, minus, and we would say plus 2x and minus x for N2 and minus 3x for H2, and again those 2's and 3's come from those coefficients up here as well. If you did the second one, it'd be a similar sort of thing, except you'd be writing partial pressures and plugging those numbers in, but that's that problem. Now let's slide down here and look at some of these problems, and what I'm going to do, I guess, is see if I can make myself a little more space. Move this block of problems down further. Here, get us a little more writing space. Alright, so that's a little bit more. We'll probably have to reclaim more again. So, okay, so starting up here with number 57. When heated, iodine vapor dissociates according to this equation. I2 gas is in equilibrium with 2 iodine atoms in the gas phase. And we're told that at 1274 Kelvin, a sample exhibits a partial pressure of I2 of 0.1122 atmospheres and a partial pressure due to I atoms of 0.1378. Determine the value of the equilibrium constant. So what they're giving us here, these are the equilibrium values. So all we got to do for 57 is say that Kp is equal to the partial pressure of I squared, and again that squared comes from that 2 right there, and the partial pressure of I2 on the bottom. So we have 0.1378 quantity squared on the top and 0.1122 on the bottom. And if we do that math, and no, I'm not going to try to do that one in my head, 0.1378 squared divided by 0.1122, I am getting 0.169 for that answer, for that Kp value for 57. So not too much of a problem there, pretty straightforward thing. Let's look at 58. 58, we've got a sample of ammonium chloride heated in a closed container. So we've got a heterogeneous equilibrium here. We've got something that's solid, so it's heterogeneous. We're told at equilibrium the ammonia pressure is 1.75 atm. What is the value of the equilibrium constant Kp for the decomposition at this temperature? Okay, so it looks like we're missing something, right? If we think about our ice chart for this guy, so I'll write ICE for this, we have ammonium chloride, but it's solid, so we don't really care about its values. Then we have ammonia, and we have HCl. And we do care about those, and initially, presumably, those are 0. Now, if you calculated Q for that, you might not be surprised to find that that value is 0, that we need to have more products. And obviously, if something on the product side is 0, you got to have pluses over there because you can't have negative stuff. If I had negative X there, it would mean ammonia's concentration was going to 0. So our equilibrium line is 0 plus X, or just X. And what we're told is that X is 1.75 atm. Well, that's the same X for HCl here. So our Kp for this one is going to be, we're going to have just the ammonia value times the HCl value. And I'm sorry, those are partial pressures. And I wrote Kp, you'd think I'd get that. So P sub NH3 raised to the first times P sub HCl raised to the first. So that's going to be 1.75 times 1.75. And that I ought to be able to do in my head. It's going to be a little less than 4. 3.06 is our value. 3.06 is what I get, and that's the Kp for, again, question 58 there. So that's 58. Make sure that's clear. And then that's 57. All right, so slide it on down here, and we'll take a look at problem 59 here. Clarify that up a little bit so I can see what I'm doing. All right, we're told the vapor pressure of water at 60 is 0.196 atm. What's the value of the equilibrium constant Kp for the vaporization equilibrium at 60? So our data at 60 and our Kp at 60, those are the same. That's good. We can use that. So 59 here, we've got H2O liquid in equilibrium with H2O gas. This is just the vaporization of water. Our Kp for this is going to be equal to just the partial pressure of water gas, because we leave out the liquid since it's pure liquid. So it's a heterogeneous equilibrium. Again, those rules apply. What we're told is that value is 0.196 atm. So again, we won't use the units, but Kp is 0.196. It's that easy. It's just the actual value they gave us. So again, this little box here is all of 59. And then for 58 here, I'm sorry, for 60, we've got we're doing here, we have 2 SO3 in equilibrium with 2 SO2 plus O2 gas. Everything's gaseous there. Seen this equilibrium before in some of our talks. And what we're looking at really here is the change line. One version of it is in algebraic form. The other one is giving us a version in actual numbers. So what we're given is plus X over here, and we're told that that's 0.125 molar. All right, so that again, it's the changed line, and we're looking at it both ways. We're looking at it as in terms of X, and we're also looking at it in terms of actual numbers. So from the first change line, if O2 is plus X, then SO2 must be plus also, because it's a product. And so if one product's plus, the other product's plus 2X for SO2. and then we're going to have minus 2x for SO3 because it's going down. It's a reactant. So if 0.125 is the value of x, then 2 times that is 0.250 molar, and negative 2 times that is negative 0.250 molar. So there's more of those in the book that you could look at, but that's what you're looking at there. Again, it's two different versions of the change line, one in terms of x, one in terms of real numbers. All right, let's skip on down here and take a look at this one. Maybe I'll use some of this space up here. So this is jumping down a little further. What we have here is an equilibrium problem where water is reacting with chlorine oxide, dichlorine oxide, and forming 2 moles of, that would be hypochlorous acid, HOCl. And we're given initial conditions, and we're asked to figure out what the equilibrium conditions are. So 77, I'll work up here. We're going to make an ice chart. We'll have H2O, Cl2O, and HOCl. And initially we've got 1 molar of this, 1 molar of that, and 0 HOCl. They don't actually come out and say that, but that's what's implied, that the mixture starts off with just the reactants. Now, if we calculate Q for this, Q is going to be 0 squared, that's the HOCl part of it, divided by 1 times 1, that's the H2OClO part of it. That's going to be 0. And that tells us that that's less than the Kc, which we know is 0.090. So that means we're going to increase our products and decrease our reactants. So negative, negative, plus on the C line. And then the stoichiometry, the coefficients tell us that we lose 1x in water, 1x in Cl2O, and we increase 2x in HOCl because that 2 right there gives us that. All right, so at equilibrium, we're going to have 1 minus x on the E line for both H2O and Cl2O, and 2x on the HOCl line. And so we'll write our equation. We're told that Kc is 0.0900 is equal to, so I'm going to put the values in, 2x is squared over 1 minus x squared, and what those are representing, of course, is HOCl concentration squared, and then the H2O concentration times the Cl2O concentration. Again, this is a gas phase, but we can talk about that. So the reason this term over here that I just highlighted in yellow, that's squared because these two are the same. We multiply those two together and we wind up with that. Now, this is the problem we got to solve right here in this little box. Got a little algebra problem at this point, and you may look at that and say, "Oh my gosh, that's a quadratic. It's going to be hairy. I've got to do a bunch of algebra." Not so much. Actually, there's a short way to solve this one. If I take the square root of both sides, so the square root of 0.0900 is going to be equal to the square root of 2x quantity squared over 1 minus x quantity squared. Well, what that means is that's equal to 2x over 1 minus x. We just get rid of that. And the square root of 0.09 is going to be something like 0.3, I think. 0.09 square root, yeah, 0.3. So that side of it here is 0.3. So we wind up with a much easier equation. And we're basically saying that 0.3 is equal to 2x over 1 minus x. I always say if you were offered that equation as the final exam for your math course, you'd probably be pretty happy because you can probably do this one. We cross multiply. 0.3 1 minus x is equal to 2x. We then distribute the 0.3 through that, so we have 0.3 minus 0.3x is equal to 2x. Then we add 0.3x to both sides. And we wind up with 0.3 is equal to 2.3x. So x is equal to 0.3 divided by 2.3. And if I calculate that, I get that x is 0.13, and we'll go with that. So if x is 0.13, I can go back up here and say this is 1 minus 0.13, 1 minus 0.13, 2 times 0.13. So this is 0.87, this is 0.87, and this is 0.26. So this is my, again, my E line here. And again, what I've done is I've taken this value right here and run all the way around here and plugged it in to get that. I would check my answer. What I'm going to do is I'm going to check, is that value equal to 0.26 squared over 0.87 squared. I'm just plugging it back into the Q expression. And I get basically 0.0893, and that's close enough. That's good. That's about within that 5% error that we have. So that's my check where I plug those values back in. If that didn't make sense, feel free to rewind this video and walk through that one again. Hopefully that will help. But that's an example of an equilibrium problem where you work through all this, you get yourself a what looks like a quadratic, but actually it simplifies into something nicer. All right, looking at number 78 down here, we've got H2 plus I2 in equilibrium with 2HI. We're told that the K is 50.2, and we're not going to worry about the temperature as long as we know we're working with that. We're asked to calculate the number of grams that are in equilibrium with, okay, so what they're telling us is our E line, and what we know about the E line is that we have 1.25 moles of this and 63.5 grams of that, and we're being asked how many grams of HI do we have. Well, so there's some issues with this problem. One issue is that normally we deal with molarity, right? For a KC we deal with molarity, and the authors of this textbook seem to have not stated what the volume of this container is. I'm going to assume that the volume is 1 liter. Okay, that's probably what they meant to say, else this is really not going to make any sense whatsoever. So we want to think about our values here in terms of molarities. So 1.25 moles divided by 1 liter is pretty easy. That's 1.25 molar. All right, so that's our hydrogen. Now iodine's a little tougher. We're going to have to say 63.5 grams of iodine. We're going to convert that to moles. 1 mole of I2 is, well, let's check our periodic table. So let me shift back here to, guess we'll go all the way back to the general and look at the equation sheet here and see if we have our periodic table. Oh, there we go. And looking at iodine, that's about 127. So going back over here to our problem that we were working on. So this is 127 times 2 is 254 grams per mole of I2, roughly. And that'll give us moles of I2. And so if I do that calculation, it's looking like it's about a quarter, isn't it? 63.5 divided by 254. Yeah, exactly. A quarter mole, 0.250 moles. So again, if we look at that divided by 1 liter, that's 0.250 molar, so we'll say 0.25 here. So now we can figure out what the molarity is for HI. So we'd say that Kc is equal to 50.2. That's equal to, I'll put the numbers there. And then what I'm writing here though is HI squared divided by H2 times I2. So H2 we know is 1.25. I2 we know is 0.25. And we don't know what HI squared is, so we'll just call that x squared. So this becomes our little algebra problem, and of course that's quite straightforward. X squared, or x, is going to be the square root of 50.2 times 1.25 times 0.25. So 50.2. So 50.2 times 1.25 times 0.25, I get 15.68 for that. I take the square root of that, I get 3.96 is my molarity. Now, that's not the answer to the question. They want grams. Let's just check about Kc. What's Q if I say 3.96 squared over 1.25 times 0.25. So I'm going to square that, divide it by 1.25, divided by 0.25. All right, what number should I get? I should get pretty much the K value, and that's what I get, 50.2, which is equal to Kc. So that's my check. My calculation looks okay. So then to get to grams, okay, if I have 3.96 moles per liter, and I've got 1 liter that I've assumed, and then this is HI, right? So HI is going to be basically 128 grams of HI per mole of HI. That's our calculation there. You can see we can cancel a few things out here, moles and moles, liters and liters, and we'll have grams of HI. So 3.96 times 128, I get 506.88 grams of HI as the answer to that problem. Switch colors again. All right, so that was all 78. Let's look at 79. 79 says butane exists in 2 isomers, N-butane and isobutane. These are compounds you're going to see in organic chemistry. And we're asked, we're told the Kp is 2.5, and we're asked what the pressure of isobutane is in a container of 2 isomers at equilibrium with a total pressure of 1.22 atmospheres. So I want to pick this one out and show you because it is a little bit of a weird, different problem. So let me come down here and write some information. So 79, we've got N-butane in equilibrium with isobutane, which looks like that, right? I'm kind of drawing that. And Kp is 2.5. So this is N-butane. This is isobutane. And we're told that the total pressure at equilibrium is 1.22. So at equilibrium, the total pressure, and of course the total pressure is going to be the pressure of the N-butane, I'll write NB for that, plus the total pressure of isobutane, so I'll write isoB for that. That's going to be 1.22 ATMs. So let's look at our problem. We don't really know the initial, we don't really know the change, but let's just play with this. Let's say that we had, if we did an ice chart, so N-butane here, I-butane here, ICE. If we started out with, let's say we start out with Y amount of N-butane and 0 IB. We're going to go up X here, go down X there. So this would be Y minus X, and this would be X. And at equilibrium. And of course, what this tells me here, my total pressure, Y minus X, P total is PNB plus PIB. That's going to be Y minus X plus X. That's just Y. And so I've identified that the total pressure was 1.22 atmospheres. And that the initial pressure would have been 1.22 atmospheres. So now what I have to do is figure out what X is. So I'm going to rewrite my E line now as 1.22 minus X plus X. And I'm going to write my equilibrium. My equilibrium is Kp. Of course, that's equal to 2.5. We were told that. And that's going to be equal to the isobutane on the top, that's X, over 1.22 minus X on the bottom, that's the N-butane. So again, concentration of isobutane on the top, concentration of N-butane on the bottom. And I know that looks weird, but you'll get used to that nomenclature system when we get in organic. So again, what we're focusing on here is this little algebra problem in the middle. And it's not too bad. 2.5 times 1.22 minus X is equal to X. So 2.5 times 1.22 is going to be something like 3. That's 3.11. Minus 2.5x is equal to X. And then we'd say add plus 2.5x to each side. So we wind up over here with 3.11. Over here we wind up with 3.5x. And so x is going to be equal to 3.11, 11 divided by 3.5. And that comes out to be 0.89 basically. And so if we look back at our E line, that will be our partial pressure of our isobutane. Our partial pressure of our N-butane is going to be 1.22 minus 0.89. That's about 0.33. And those are ATMs. I don't remember which one we were being asked about. Slide back up here and take a look. Let's see, read the problem. What is the pressure of isobutane is the actual question. So the answer that we're looking for down here is this one. That's the pressure of isobutane. A little harder problem. You had to go back up here and recognize that you had this relationship that you could establish that the total pressure, which was the sum of the N-butane and isobutane, that if we made this assumption about an initial value y, we wound up with just being able to create a really simple equation here and figure out what that value was, and then plug that in and follow the algebra. Again, no individual step in that's hard. What's the tricky is putting all the pieces together. All right, I hope those helped.